Welcome back. This is the first segment of section 4.2. As you'll recall, in section 4.1, we talked about the graph of sine of x and cosine of x, and then we looked at modifications to it, which are traditionally called the transformations, either a vertical stretch or shrink, which is represented by the letter A in our sort of master formula, and then a horizontal stretch or shrink, which is represented by the letter B in our master formula. So in section 4.2, we're going to continue using the sine and cosine function as sort of the basis for looking at the remaining parameters, which are the translations, which is, for lack of a better term, is literally moving the graph around, moving the function graph around on the coordinate axis in a very prescribed way. So let me kick it over here to the document camera, and we will sort of start into this. Okay. All right, so this is section 4.2, and this is the first page. Okay, so and I think I want to just sort of preface this by saying this is what we were talking about exclusively in section 4.2 is translations. Now we're going to introduce both a horizontal and vertical translation, and then we're going to come back and we're going to look at sort of putting all of that together. So taking an equation with all four of those parameters in place, and how to sort of bring that together. And then at the end of this, we will actually take a graph, sort of a generic graph, and maybe even one that's fairly complicated, and try to come up with a way to generate the equation for it, which is actually the more complicated skill. So for now, translations. So let me just make a statement here. For any function f that is graphed so that is y equals f of x, when y is equal to f of x minus c for some real number c, not equal to 0, because if it's 0, it really is no different than f of x. But for some real number c that is not equal to 0, the entire graph will be shifted horizontally and it will be shifted to the right if c is greater than 0. So if you think of like the coordinate axis as being fixed, and if c is a positive number, then you would take the function, the graph of the function, and simply shift it to the right by c units. It will be shifted to the left if c is less than 0. So if c is a negative number, the negative sign on c. Now recall, there's a negative in here. So if c is negative, then this whole term is x plus some number, and that's kind of critical. So we look at c as being positive numbers shift to the right, negative numbers shift to the left, but don't forget about the fact that there's actually this negative number up in here. So let's take an example. I'm going to graph for you the equation y is equal to sine of x plus 3 pi over 4. Okay, so first, note that c is equal to negative 3 pi over 4, right? So you got x minus a negative 3 pi over 4. So if we start by, and what I always find, most students who are first getting into the swing of graphing trigonometric functions will actually draw the graph, the coordinate axes first, and then draw the graph on top of it. And the problem with that is you don't always necessarily know what the parameters are, what it's going to look like before you start. And so you can end up with a graph that is really impractical for what you're actually trying to graph. So what I do is I just start by graphing the function without any coordinate axes, and then I put the coordinate axes on them. So let's just sort of draw a sine function. And I'm actually going to draw 2 periods of this thing. Okay. And recognize, now we haven't talked about horizontal translations at all, or sorry, vertical translations yet. So I'm just, because that's the case, that this will lie at the sort of baseline of the sine function will lie on the x-axis. So I'll just go ahead and throw an x-axis in there all the way to the right. We don't exactly know where y is, but what we do know is that we've taken a sine function, we've shifted it to the right by to the left by 3 pi over 4, which means that this point, which would normally be the y-axis, would sit on this point. This is actually negative 3 pi over 4. Okay, so now we don't have a modified period because there's no b value out here. B value is assumed to be 1. So what does that do for us? Well, that tells us that this distance from where we are at 0 here to this next 0, we know that the period of this function is 2 pi, and so this must be 2 pi ahead. So if we add 2 pi to negative 3 pi over 4, what we end up with is 5 pi over 4. And similarly, if we look at this next point, add another 2 pi to this, we end up with 13 pi over 4. Now, you can make a guess as to where the y-axis should be sitting, but I'll sort of spare you the suspense. It's actually about half, so it's 3/4 of the way between these two zeros. So you have quarter pi, quarter pi, quarter pi, quarter pi. That's 4/4. So this would be this 0 occurs at positive pi over 4, and then quarter pi, quarter pi, quarter pi, quarter pi, and 5 pi over 4. So this position, about 1/4 of the way, or sorry, 3/4 of the way from this 0 to that 0, is where the y-axis will be sitting. And you could label some points if you want. It's not super critical to do that if the axes are labeled properly. The only thing that we're missing with this is we need something to represent the amplitude. And because the a value is 1, the amplitude here will be 1. And so these sort of upper and lower bounds will be 1 and -1. So this is a sufficient graph for this function. It has enough information on the x-axis to determine both the period and the horizontal shift, and it has enough information on the y-axis to determine the amplitude. This is sort of minimal for a graph of this kind. Okay, so this is how the horizontal shift works. This is a little bit harder to visualize than the vertical shift, which is actually probably the simplest of all the transformations and translations. It's strange how we kind of go from hardest to easiest, but so be it. So remember, this is going to be the parameter designated by the letter D. So before we get there though, I want to combine up a couple things. I want to do one more example of maybe a couple more examples of some graphs involving both this horizontal translation, but maybe also something with an amplitude. So let's let's do another graph. So let's graph the equation y equal -2 cosine of x minus pi over 3. Okay, so now this graph is shifted to the right. So maybe if I peel these off, a equals -2. So this tells us the amplitude is 2. And b equals 1. That tells us the period p equals 2 pi. And c equals a positive pi over 3. Remember, this is, again, I know I'm bringing this up several times, but that negative sign, it's x minus c. So c is actually positive pi over 3. This means a shift to the right by pi over 3. Now, one other thing I want to note here about A is notice that it has a negative sign. So I'm going to maybe put a little note to myself that it should be reflected. Okay, so again, what I'm going to do is I'm going to just draw the basic cosine function, which looks exactly like the sine function. We just need to pick some different points for our start. So I'll kind of start with a low point, and then high point, complete the period, okay? And then again, I'll do one more. And maybe just stop right there at a high point. So again, we haven't gotten to it yet, so there is no vertical translation at all. D is actually equal to 0 in the big equation. So the x-axis will lie right down the baseline. It's either side of this graph. Now, here's where it's kind of critical to note that this is reflected. So recall the origin of the cosine, the unadulterated just y equals cosine of x, starts with a high point, right? But because this is reflected, it will actually start with a low point. So this point right here, or this one, but we'll stick with this one, represents the shift to the right by pi over 3. So this point, the x value here, is pi over 3. And note that the next high point, which is half the period, will be pi, and it will be a distance on the x-axis of pi from this point. So this will be 4 pi over 3. The next low point, which is a full period, will actually be 7 pi over 3. And then finally, this high point will be 10 pi over 3. Now, if we went backwards, this point back here would actually be -2 pi over 3. And so that gives us an indication of where the y-axis should be. It should be 1/3 of the way between these two, or sorry, 2/3 of the way from this one to that one. So we're sitting right about there. Now, the only other question to be concerned with is about the amplitude. So note that because A has the absolute value of A is 2, the amplitude is 2, which tells us this thing oscillates between -2 and 2. So if we were to label, if you will, this coordinate, this is not really necessary for the graph, but its x coordinate is 4 pi over 3, and its y coordinate is 2, right? And we could do that for other points on this graph, but it's not necessary to do that, but that does kind of help you visualize what's going on there. Okay, so let's try one where we also have a modulation. We have a b value that's not 0. And I don't know that I used this term previously, but The B value is related to the frequency, which is another physics term. But the frequency is the reciprocal of the period. So, really, I don't want to confuse those two ideas. But what I will point out, since I forgot to mention it, this C value, when you're talking about a physical application, C is sometimes called the phase shift. And I know that's kind of a weird term, but I'm going to throw it out there because I think you see it in the textbook mentioned. So C is sometimes called the phase shift. It's also called the horizontal translation. The horizontal translation makes more sense, but the phase shift is something that's actually used in physics quite a bit. Anyways, so let's try another graph. Let's graph the equation. This one will actually have both a frequency modulation and a phase shift. So we've got y equal to 3/2 cosine of 2x minus pi. Okay, now I'm going to actually probably graph this on the next page because I'm running out of space here. But here's something that I want to point out. The textbook, anytime there's a b value that is not equal to 1, the textbook always does this to you, where it doesn't actually factor this out. Remember, the equation we had was y equals a times f of b times x minus c. So we have to factor out this 2, which means we actually have to factor it out of this pi as well. So before you do anything, anytime you see a b, it's going to do this to you almost every time in the textbook. You have to factor out this b value. So the first thing I do when I see something like this is I write it in the appropriate form. I've got y is equal to 3/2 cosine of 2 times x minus pi over 2. Now, I just want to be careful because, as it turns out, students often make this mistake. Just to verify, distribute it, because what they'll do is, for some reason, and I don't know why, but you'll double instead of taking half or vice versa. It depends on how complicated b is, and it especially starts to become cumbersome when b happens to be a fraction. But just if you want to make sure that you've got the same thing, just distribute this and make sure it's the same argument. Right, but you have to have it factored to be able to adequately talk about the c value. So here we have a is equal to 3/2, and recall that that's the amplitude. B is equal to 2, and so from this we have that the period is equal to the normal period for cosine divided by the b value, which is 2, which is just pi. And then c is equal to positive pi over 2, remember that negative sign, which indicates shift to the right. And the amount is pi over 2. So to graph this then, I'm going to just go ahead and repeat well, I have the equation. So all right, page 3 here. So again, I'm going to graph the equation y equal to 3/2 cosine of 2 times x minus pi over 2. Okay, so again, I'm going to put the axes on after the fact. So I'm going to start by drawing the basic shape of a cosine function. And I'll go ahead and draw 2 periods at least. And again, there's no vertical shift, which we haven't really talked about yet. So the x-axis will coincide with the baseline. Okay. And recall, cosine has a maximum, normally has a maximum where the y-axis is at. And since it's not reflected, we will look to this first maximum to determine position. So it's, because the amplitude is 3/2, that will be the y value at this point. And because c is pi over 2, the coordinate of this point will be pi over 2, comma, 3/2. Okay? And because b is equal to 2, the period is equal to pi, we can figure out what this point is over here. This is a full period, so it'll be an additional pi. So pi over 2 plus pi is actually 3 pi over 2. And this is pi over 2. So that actually makes this point in the middle pi. And if we were to extend this just a little bit more, I think I didn't, I kind of started too far to the right, but if we get that minimum will actually be at the y-axis. Right, so we have each one of the quarter points of this function is a unit of pi, or sorry, a unit of pi over 2. Okay, so the last thing left to do is to plug in the ranges on the y value. So this is, since the amplitude's 3/2, this thing will oscillate between -3/2 and 3/2. So this is 3/2, and down here will be -3/2. So there is sort of the minimal graph of this equation. Okay, so let's talk about vertical translations now. Or vertical shifts sometimes. So a vertical shift when d is a real number and d does not equal 0, the graph y equals f of x with the d outside the parentheses plus d is shifted vertically. So I guess I didn't really say that real well. If you had the graph y equals f of x and you tack on this extra little number on the backside, this whole graph will be shifted vertically, up and down, if you will. It will be up if d is greater than 0, and it will be down if d is less than 0. So now that we have both of these, both the horizontal and vertical shift combined together, it turns out that we can do something kind of interesting with these graphs. So I'm going to do this by way of example, but I think I'm getting, well, this is not a very long section, so I'm just going to kind of introduce this idea, and then I'm going to do a couple of examples. I'm going to graph this. I'm going to give you an example equation here, and then I'm going to graph it. And then I think we're going to call it quits for a minute. We'll come back with the second section where we do some stuff involving taking a graph and producing an equation. So let's, as an example, let's graph the equation y. We're gonna add a couple of features in here. So y equal to 3 cosine of 2x minus 2. And it's important. Here's where you start to get confusion. If you don't use these parentheses, it could be 2x minus 2, close parentheses here. It could be a vertical shift or a horizontal shift. There's a little bit of ambiguity. And so I always try to use the parentheses to indicate what the actual argument of the function is. So let's shift to a new page here. And we're now on page 4. I'll probably continue. I won't use this entire page, so I'll start our second segment on this page. So again, the equation is y equals 3 cosine of 2x minus 2. Note that a is equal to 3. It's not reflected, so this is amplitude is equal to 3. B is equal to 2. So just like before, the period is equal to pi. I won't repeat that calculation. Remember, that's P is equal to P naught over B. P naught, in this case, is 2 pi, and B is 2, so you end up with pi. C equals 0, so there's no horizontal shift. And D equals -2, so it's shifted down by 2 units. Okay, so let's again, as I suggested, let's just draw a cosine function. Draw a couple periods here. Okay, so now we're not going to draw the x-axis because the x-axis is actually, we're shifted off the x-axis. But maybe what we could do is plot a couple points. So because there's no vertical shift, or sorry, no horizontal shift, this could represent the starting point. So the y-axis could be right here at that high point. And so this coordinate is an x value of 0. And so here's what we have to think about. This thing is shifted down by 2 units, but it has an amplitude of 3. So that means that the sort of baseline is down 2 units, but the d value is but the maximum is actually at a value of 1. Okay, so this point over here, which is exactly 1 period away, so its x value will be pi, also has a y value of 1. Now, like I said, it's not critical to plot these points, but it does help us kind of figure out what's going on. So this low point, I know I didn't draw it real well. This low point is halfway between these two. So this point down here is actually pi over 2, and now the y value, note the baseline will be at -2, and it drops 3 units. So this has to be -5. And between these 3 points, you can pretty much figure out exactly where the x-axis is. It's most of the way here. Right? And then maybe we could put some labels on here. It goes from 1 to -5. Maybe you could put, maybe some other ones in there. It's no big deal. But this is sufficient for the y-axis. And then we have pi here. This is pi over 2. So this is actually -pi over 4, but whatever. This minimum down here is actually 3 pi over 2. So this isn't quite, I don't have labels out for 2 periods, but this gives you sort of an idea what this looks like. And again, my graphing skills are terrible. So I'm going to leave it at that for the time being. I'll be back with another segment here briefly. Like I said, section 4.2 is pretty short, so I think we'll only get 2 segments out of this. Okay, see you soon.